The physics of ore. How can the ore system have 95% efficiency? This needs an explanation from the perspective of first law of thermodynamics. The atmospheric wind extractor is not a traditional wind turbine. To comprehend the ore system's energy harvesting efficiency, you have to first understand that the ore is not a conventional wind turbine. The evaluations of the ore must not be confused with those of conventional wind turbines. The energy capture properties are much different. Ore efficiency. Here are a few elements that support efficiency claims. Wind turbine technology says that one can't change the wind speed, so the only recourse is to make the wind turbine higher and bigger to capture more wind power. Ore technology says this is the fundamental flaw in wind turbine technology thinking, that the wind produces the power. In reality, the force of the weight of moving air produces the power. Wind only moves the air. Energy available for harvesting. The ore design makes possible two main external energy sources, wind impulse force and tangential speed air flow. Wind impulse force. The wind is an obvious external energy source that varies in magnitude with the wind speed. The force of the wind is applied to one side of the closed drive panels, upwind side. This provides an impulse that while the wind is blowing the structure will rotate. Tangential speed air flow. This is separate and distinct from the wind. The positioning of energy capture units on the rotating structure is by design, radially outward from the center of rotation to subject the energy capture units to tangentially amplified speeds. The further outward from the center of rotation, the faster the tangential speed and the greater the amount of energy available for capture from the airflow. GE 1500 kilowatt wind turbine. We can discover the efficiency of the wind turbine using the same power of the wind formula and the manufacturer's own data. Ore relies on airflows and not the actual wind speed, as well as circular motion circumference. An ore device uses this phenomenon to increase the speed of air flowing through energy capture devices connected farther out from the center of rotation. Or wind harvesting. The 1500 kilowatt wind turbine generates 1500 kilowatt-hour at a wind speed of 25 miles per hour. At 25 miles per hour or 11.18 meters per second, the turbine has a potential kilowatt per hour of 4,727. Utilizing Betz's law at 59.3%. The turbine only converts 51.3% of the potential energy or 1500 kilowatt-hours. Using Betz's law, the results of the wind power formula calculations for both the wind turbine and an ore model reflect the dramatic difference between the two technologies. Applying the same percentage converted to electricity to the potential energy capture utilizing a 5 megawatt ore system. At 25 miles per hour or 11.2 meters per second, the turbine has a potential kilowatt per hour of 877,580. Utilizing Betz's law at 59.3%, the potential is 520,405. The rated capacity at 25 miles per hour or 11.2 meters per second is 278,472 if the ore system converts 51.3% of the potential energy that would result in a theoretical rated generation capacity of 13,456. Obviously, an ore device will not generate 20 times its generator capacity. But this illustrates that an ore device would have to be 1/20th as efficient as a wind turbine in converting wind energy into electricity, or only 2.59% efficient to generate 100% of its generation capacity. Of course, that capacity is 9 times greater than that of the wind turbine. Energy harvesting and conversion efficiency. How much energy is available to be harvested? This is at the core of the fundamental difference in the way ore approaches using wind. The wind represents a flow of air whose mass at a given speed produces energy that can be captured and harnessed. The greater the speed of the air flow, the greater the amount of energy available for capture and harvesting. The density of air varies with altitude and other climatic conditions, but at any specific site at any specific time this would be a constant. The swept area of the rotor is fixed to the actual design of the device, that is the area of the circular path of the blades, or in the case of the ore the area of the closed panels, blades of the flutter vanes, the area of the circular path of the blades of the propeller units. The example of a 5 miles per hour wind speed, 2.24 meters per second, which when cubed equals 6.88 watts per square meter of swept area. The example of wind turbine hub height adjusted wind speed, 3.02 meters per second, when cubed equals 16.94 watts per square meter of swept area for the one rotor area. The or-closed drive panel hub height adjusted wind speed, 2.464 meters per second, when cubed equals 9.16 watts per square meter of swept area for the one rotor area. The capture and harvesting devices mounted to the oar have the additional following power available based on the tangential speed airflow. The tangential air speed multiplier is a factor based on the radial distance of the device from the center of rotation divided by the radial distance of the tower-mounted bearings. The adjusted tangential airflow speed is then cubed and multiplied by the power formula factors 0.5 and 1.225 to determine the watts available. The 6 flutter vanes, the propeller units, and the main flywheel will have more than 645 million watts available. Comparing the total watts available to the wind turbine per square meter of rotor area, 16.94 watts, versus the oar model 37.64, 645 million watts, illustrates the significant difference in the way oar approaches the utilization of wind as an energy source. What are the efficiency of the internal system energy conversions? When the efficiency of the internal system energy conversions is considered, we derive the individual efficiencies of each oar element. Wind rotor, 98%. Rotor to flywheel, 98%. Flywheel to air compressor, 97%. Compressed air piping and storage, 95%. Compressed air to air motor, 95%. Air motor to generator, 70%. Generator itself, 80%. The aerodynamic principles behind the flutter vanes. The flutter vanes do not produce electricity. The flutter vanes and the compressors attached turn a flywheel, which in turn is attached to a radial compressor. The compressor produces compressed air. That compressed air powers an air motor which is released at 90 psi and powers the generators. These wind and tangential air flow harvesting devices can operate without the drive panel structure rotating. The flutter vanes 3 curved panels will rotate in a 2 miles per hour, 3.2 kilometers per hour wind. Flutter vane air compressors are housed below and are operated in series using clutch systems to engage each compressor based on the airflow speed. In a 2 miles per hour wind with no structure rotation, only one compressor is operated and the compressed air is piped to storage tanks housed within the propeller units. The curvature of the flutter vane blades in the 3-blade configuration sheds a portion of the airflow striking the convex curvature into the concave section, increasing the impulse. The airflow striking the convex curvature creates lift in the direction of its rotation during a portion of the rotation to augment the impulse. The coefficient of drag 1.28 of the concave shape versus the coefficient of drag 0.295 of the convex shape lends itself to a differential of force impact to cause the imbalance, creating the rotation.